Can a spinning bumper car carry a torque? The answer to that question is no. The spinning bumper car carries angular momentum, but it can't carry a torque. As you've probably guessed, the story I'm about to tell you is the rotational equivalent of the translational story I told in this episode's first video. Like a force, a torque is exerted by one object on another object, so a single object can't carry a torque. But there is a physical quantity of rotational motion that a spinning bumper car does carry, a capacity to make other things turn in the direction the bumper car is turning. That physical quantity of rotational motion is called angular momentum. And angular momentum is the conserved quantity of turning. As required of any conserved quantity, angular momentum can't be created or destroyed. It can only be transferred between objects. So one bumper car can transfer angular momentum to a second bumper car. Fortunately for us, angular momentum has many similarities to ordinary, or what is called linear momentum. Still, those two are separate quantities, and they're conserved separately. And a bumper car carries both of them simultaneously. So I can send this guy along with momentum, angular momentum, and both. Out of control. There we go. Together with energy, a bumper car can carry three conserved quantities all together. And those three conserved quantities determine much of how the bumper car behaves. Like linear momentum, angular momentum involves motion. There is no such thing as potential angular momentum. A bumper car that's turning around some center has angular momentum, and one that's not turning about that center has zero angular momentum. Angular momentum is also a vector quantity. It's about rotation, and rotation is a three-dimensional activity that requires direction. I can rotate like this, I can rotate like this, not very far, but you get the idea that rotation is complicated in three dimensions, and so you have to specify it with direction. And just as angular velocity has a direction, so angular momentum has direction, and you use the same rules. Now, I can show you the direction of angular momentum in a single bumper car by choosing as the center of rotation the bumper car's center of mass. That's sort of the natural center of rotation for the bumper car. And I'm going to give it first angular momentum upward, like this. Here it is. It has angular momentum upward. And now I'm going to give it angular momentum downward, like that. And it's got all the variety of a vector quantity, upward, downward. I could, in principle, I can do toward me. There's toward you. Not very good for a bumper car. And finally, it has an amount. This is a little bit of angular momentum upward, and this is a lot of angular momentum upward. Always about that center of rotation, which is the center of mass of my little lone bumper car. Well, to show you more about angular momentum, and in particular that it's a conserved quantity, I'm going to return to the classroom and go for a spin myself. So here I am in a classroom, and I'm going to sit on this swivel chair, which is the rotational equivalent of the wheelie cart that I used for linear momentum. This swivel chair spins so freely, or so nearly freely, that I can't exchange any angular momentum about my center of mass with the Earth. And it allows me to kind of coast in terms of angular momentum. The angular momentum that's in me won't leak out very quickly into the ground. There are issues of air resistance too, but basically I can show you that my angular momentum is conserved. Now I'm having trouble trying to look at the camera because this thing swivels so easily. And I can't get started turning without something investing angular momentum in me, because I can't create angular momentum. Whatever I've got, I've got. Now I've got some slight little rotations going on here that have to do with the imperfections of the system, but basically my angular momentum is zero right now. And to get some angular momentum, I need to obtain some from the ground. So I'm going to put my foot down, and I'm going to have the ground twist me. It's going to exert a torque on me, and I'll get some angular momentum. Here we go. Ready? I'm going to get some angular momentum. I've got it. And now that I got it, I can't get rid of it. I got to keep going. This is a little less pleasant than coasting across a room. I'm going to get awfully dizzy, so I have to get rid of my angular momentum. And the way I got to do that is by giving it to something else. So I'm going to give it to the ground with my foot again. Ready? There we go. I gave it to the ground, and I wish you guys would stop moving. All right, so that was angular momentum upward. Now I can get some angular momentum downward by twisting the ground the other way, having it twist me back, and woof, I've got angular momentum. It's now downward. I've got downward angular momentum. And I can't stop, I can't stop, I can't stop until I give it away. There we go. Woof. And angular momentum's got a direction, and the same kind of ideas apply as with linear momentum. That if I want to reverse directions, I need a huge transfer of angular momentum. Because not only do I have to come to a stop and get rid of my initial angular momentum, I have to reverse, go the other direction around, which requires still more exchange of momentum with the ground. So, to show you that more concretely, let me get some angular momentum upward. Here we go. I've got it now. A little less, so I'm not quite so dizzy. And now, in order to reverse my direction, I'm going to have to give all my upward angular momentum to the ground. Here we go. And I have to give more than I had in reverse directions. So I gave the ground more upward momentum than I actually had, and I ended up with a deficit of upward momentum, which is to say downward momentum. And here I am, rotating downward. So angular momentum is a conserved quantity. Once you're isolated and you can't exchange with anything, whatever you've got, you've got. It's trapped in you. And to exchange it, well, there's a mechanism for exchanging it, and that will be the subject of the next video. My angular momentum depends on two things, my rotational mass and my angular velocity. And it turns out to be proportional to each of those quantities. That is, the more rotational mass I have, the more angular momentum I carry. Or the more angular velocity I have, the more angular momentum I carry. Actually, angular momentum is equal to rotational mass times angular velocity. So if I bring myself in close to the center of rotation and shrink my rotational mass, then I have a small rotational mass, and if I rotate very slowly with a small angular velocity, then the product of a small rotational mass times a small angular velocity is quite a small angular momentum. On the other hand, if I increase my rotational mass by spreading myself out far away from the center of rotation, now, even at the same angular velocity as before, I'm carrying more angular momentum. Or, if I go back to my original rotational mass and spin faster, again, I'm carrying more angular momentum. Where things get interesting is, if I have a certain angular momentum invested in me by the ground, and I change my shape, I can change my rotational mass. I'm not a rigid object. If I change my rotational mass, but I don't exchange angular momentum with anything around me, my angular momentum has to stay the same. So if my rotational mass changes, then my angular velocity has to change to compensate in order to keep my angular momentum constant. This is actually a fun demonstration, one you've seen before. I'm going to do it in the physicist version, but you've seen it as the ice skater trick if you've watched ice skaters spinning. If I start spinning with my arms out and these massive dumbbells in them, I have a huge rotational mass. And even when I'm turning relatively slowly, small angular velocity, I have a lot of angular momentum. If I then shrink my rotational mass by pulling the dumbbells in, I still have a lot of angular momentum. My angular velocity has to increase to compensate because the product of my now small rotational mass times what will have to be a large angular velocity has to come out equal to my angular momentum, which is large. So here we go. I have a large rotational mass, and so even though I'm turning slowly, I've got lots of angular momentum in me. It's upward. And now as I pull these masses in actually, I spin faster. I have to, because my angular momentum is the thing that's constant. Everything else can change, but not my angular momentum. So skaters do this trick. They start spinning with their arms out, and then they pull in tight, and they spin faster. As their angular momentum stays constant, but their rotational mass shrinks and their angular velocity increases. Well, with that then, I'm going to go back to the lab, because I'm getting pretty dizzy. It's time to stop. Wait a second, this isn't my laboratory. What am I doing here? Is this some sort of big picture moment or something? Actually, it is. I'm going to revisit Newton's first law of translational motion and rotational motion with some new insights gathered from our experiences with momentum and angular momentum. Think about first Newton's first law of translational motion. It says that an object that's free of external forces moves at constant velocity. And I'm going to make myself an object that's free of external forces, so I move at constant velocity. What underlies that law, Newton's first law of translational motion, is actually conservation of momentum. Once you're isolated, free of external forces, your momentum is constant. And because your mass can't change, your velocity can't change either. After all, your fixed momentum, the momentum of an isolated object, is equal to your mass, which can't change, times your velocity, which therefore can't change. So once I start moving along, I have a fixed velocity because my momentum is constant and because my mass is constant. So that's the real origin of Newton's first law of translational motion, conservation of momentum. What about Newton's first law of rotational motion? Things are a little different. Newton's first law of rotational motion has underlying it conservation of angular momentum. So once you're free of external torques, and I'll add the word rigid and I'll come back to it, and you're rigid, once you're free of external torques, your angular momentum can't change, so if you're rigid, your rotational mass can't change, and therefore your angular velocity can't change. So the angular velocity is constant because your angular momentum is constant and your rotational mass is constant. So your angular velocity has to come along for the ride. It's got no choice. But what if you're not rigid? Remember that word rigid in Newton's first law of rotational motion. Why was the word rigid in there? It's because if you're not rigid, you can change your rotational mass. You can't change your ordinary mass. That's really, really, really fixed. But you can change your rotational mass by changing your shape. And if you do that, first off, Newton's first law of rotational motion no longer applies to you. And second off, you do experience changes in angular velocity for a good reason. So I'll isolate myself again, so I'm separate from the whole world, and now my angular momentum is constant because it's conserved and I can't exchange with anything, and my rotational mass is constant because I'm playing at being rigid. So therefore, my angular velocity is constant. It's coming along for the ride. But if I change my shape, all bets are off. My angular momentum still is constant. But because I changed my rotational mass, I increased it, my angular velocity decreased. That is a remarkable thing that you can do in the world of rotation because you can change your rotational mass. In the world of translation, you can't change your mass, so you can't change your velocity all by yourself. Again, in the world of rotation, because you can change your rotational mass, you can actually change your angular velocity all by yourself. Just change your shape. And with that, I'm dizzy again, and it really is time to go back to the laboratory. It's nice to be back. And before I forget, it's time to pose the question that I asked you to think about in the introduction to this episode. That question was this. It says, first off, that suppose you're on a playground merry-go-round or one of these spinning platforms, and you're on the outside. And if you pull yourself to the center of that spinning playground merry-go-round, what will happen to its rotation? As you climb to the center of this rotating disc, its angular momentum won't change because that's fixed. It's an isolated object spinning about its center of mass. But you will be shrinking its rotational mass, and consequently its angular velocity has to increase to compensate in order to keep the total angular momentum of this spinning object constant. By now it should be pretty clear that once a bumper car is spinning, it has angular momentum, and it can't stop spinning until it transfers that angular momentum to something else. The riders in the car do matter because they contribute to the bumper car's rotational mass. And the more massive those riders are and the farther they are from the center of mass of the car, that is the center of rotation we have in mind for our angular momentum, the bigger the rotational mass of the car, and therefore the more angular momentum it carries for a given angular velocity. So a car filled with very massive people sitting far from the center of mass of the car, that is spread out widely within the car, can allow that car to carry an awful lot of angular momentum. On the other hand, a single child seated right in the middle of the car doesn't contribute much to the rotational mass, so that car then can turn fairly fast and still not be carrying very much angular momentum. If people move around, they can change the rotational mass of the car, and if it's already spinning, they'll affect the angular velocity of that car, according to all this stuff I've been talking about, where the angular momentum stays the same, but as the rotational mass, for example, decreases, the angular velocity has to increase to compensate. Well, most people don't set their own car spinning deliberately. That is, they don't obtain angular momentum out of the ground by driving funny. Most of the time, they wait for collisions to occur, and it's those collisions that transfer angular momentum and start the cars spinning, at least when the cars are spinning wildly. So, we need to look at those transfers of angular momentum, and that is the job for the next video.